Hey guys, I hope you all are doing good. So in the last lecture, we covered introduction to time complexity, right? We understood different types of complexities we have, which is O, theta, and omega, right? So just to give you guys a quick summary, time complexity is basically a measurement of how much time our algorithm is taking, right? We're not exactly measuring the exact amount of time an algorithm takes because it can vary based on the computer architecture or the GPU, if you're using GPU, CPU, etc., right? But we get a general idea of how much time our algorithm would take, right? So order of O, the big O is basically the worst case scenario that could happen, right? The worst amount of time an algorithm can take. The theta is the average amount of time our algorithm would be taking, right? It could be search, it could be sorting, etc. Like on average, how much time would my algorithm be taking? And then omega is basically what is the what is the best case scenario my algorithm would have, right? What is the best time my algorithm would take? And once again, we're not really measuring the time, right? We are trying to get an idea based on the input size, how would it affect the amount of time it would take? How would it affect the number of operations I would need? Right? So that's exactly what we are doing. So in this video, I want to cover some very important common complexities, right? So whenever you are going through LeetCode problems or even interviews, right, you can be asked what is the time complexity of this algorithm, right? Build this algorithm and tell me what would be the time complexity, or maybe you could be asked the space complexity, right? You could be asked questions like this is the time complexity, improve the time complexity, etc., right? So understanding these common complexities is super important to understand. So let's start with, we're going to go from the fastest to the slowest one. So basically, and we are looking at the order of n, right? We're looking at the worst case scenario. We're not considering these two, omega or theta over here, right? So the point is that we're going to understand what is the best case scenario, what is the best time complexity an algorithm could have to the worst possible time complexity algorithms have, right? That exist today. So let's start with the first one. The first one, which is the fastest one, is the order of 1. Algorithm is O1 if it takes the same amount of time regardless of the input size, right? So what this means is that doesn't matter if the size of my input increases, the algorithm will still take constant time, right? So what I'm trying to say is if you have this graph, right? Let's say you have this graph. So the point is that doesn't matter whatever, as long as if my n is increasing, the time wouldn't increase with it, right? It's going to stay constant, right? So I hope you guys understand the constant graph, right? Doesn't matter, as long as n is increasing, the amount of time will be a constant number, right? So one of the examples is int get first. So this basically, this is a function which gives us the first array element, right? It returns the ARR 0. So think about this, right? This int n would be the size of this array, right? But think about it, right? Doesn't matter if this n is 500, 600, 700, right? This algorithm is always going to return the first element. So it doesn't really care about the size. It's still going to return the A0 and it's going to perform one operation, right? Hence, it doesn't matter if the n increases, the time is still going to stay constant, right? So this is the best case scenario possible, right? This is actually what we are trying to achieve, right? Constant time. But it's not really possible in real scenarios and real world algorithms, but in some cases it definitely is, right? So this is the first one, the best case scenario. Second one is the order of log n. This is slower than order of 1, right? Constant time. It means problem size reduces by a constant factor every step, right? Example is binary search. So this is very important to understand again. What this means is that whatever the input size is, right, our problem reduces it by some constant factor, right? So I've given this example over here, right? Binary search, these arguments are, I'm taking the array, I'm taking the input size n, and this is the value that I'm trying to find. So first of all, I'll give you guys a basic idea of how binary search works, right? Binary search basically goes to the middle element, right? And it compares whatever value we are trying to find. It's going to compare x to the middle element. If x is less than the middle element, it's going to go towards the left side of the array and and get rid of the right side of the array. Otherwise, it's going to search the right side and get rid of the left side, right? So every single step, so just like this, right? Let's say you have this. Remember, binary search needs an array to be sorted already, right? Don't worry too much. We're going to get into detail into binary search, but for now, we just need to understand what does log n mean, right? So think about this, right? Let's say I have this array and I'm trying to find the value 4. So x over here would be 4, right? So what's going to do is my algorithm is first going to go to 3. It's going to compare, is x equal 3? That's not the case, right? But then it's going to see, is x greater than 3, x less than 3. In our case, 4 is greater than 3, right? So it's going to get rid of all this part. And then it's going to start searching this array over here. So the point is that every single step my algorithm is taking, it's getting rid of half of the array, right? So it's reducing the size by a constant factor every step. A lot of algorithms do this, right? For example, searching trees, etc. It might be complicated to understand as of now, but as we go into detail, I'll explain which algorithms have log and complexity and more, right? So, but the point is, it's going to reduce the size by a constant factor, right? So, for example, binary search is reducing the size by half. There could be algorithms that reduce the size by 3 times and many more, right? So, that's pretty much it for log of n, right? Third one is order of n, right? Once again, don't worry too much if you're not getting the clear idea. As we go into detail of algorithms, right, like searching algorithms and sorting algorithms, we will get into detail what is their time complexity, what is their space complexity, etc. Right? I'll go into detail of every single algorithm we cover along with their time and space complexities, right? Okay, so the third one is order of n, and this is the one that we covered in the last lecture as well. If the number of operations grows directly with the input size, right? So if input size is 500, my algorithm is taking 500 steps. If it is taking 600, my algorithm is taking 600, right? So this is the type of graph that it could be like. Right, so as n is increasing, the time is increasing as well, right? It's kind of like a straight line with, you can say, a 45-degree angle, right? So what does this mean? I've given this example over here as well. Just like consider this for loop, right? I'm just printing the values I in this case. So for int I equals 0, I less than ni plus plus, print the value I. So think about this algorithm, right? Depending on n, if n is 500, then it will print 500 values, right? That means 500 operations. If n in this case was 600, then this would print 600 values. So as long as the n increases, the number of operations increases as well, right? Actually, it is directly proportional to it, right? So this is the kind of graph it looks like, and this is what we mean by order of n, right? So one other example could be searching linear search, right? So let's say you're looking for an element inside an array, just like we considered in the last lecture, right? So let's say your array has 500 elements, and then you're trying to start from the first one going up to the last one. Right, that would mean order of n as well, right? You're taking n different operations, n steps. And as the size goes from 500 to 1000, the number of operations you would have to perform would also increase. Right? So in very simple words, you can say that the number of operations grows directly with the input size. So if n is increasing, the number of operations is increasing as well. And this is like a very basic example. Right? So quick summary of all these. O1 basically means constant time. Right? It doesn't matter how big my input size is, or if it is small, or if it is less, or if it is bigger, it's always going to take a constant time, right? Second one is order of log n. This is the time complexity in the case when our algorithm is reducing the problem or the input size by half every single step. It could be half, it could be a constant factor, right? It doesn't have to be half in general. And the third one is order of n, right? Number of operations grows directly with the input size. So this is one of the examples I've given. It's just going to go direct. It is basically directly proportional to the input size. Right? Now let's look at the other ones we have. Okay. Now let's try to understand the order of n log n and the order of n squared. Right? So this one is kind of tricky to understand, but I'll try to make it as easy as possible. Now think about this, right? You understand linear time, right? You understand order of n. Think about the last example we covered, right? So for example, the uh, the number of operations is increasing as the size of the input is increasing, right? So think about this: you have an array and you're printing all the elements. So if the array size is 500, then you're going to print 500 times. If it is 600, you're going to print 600 times. But they are kind of increasing proportional to each other, right? Order of n log. Now let's understand log n, right? Log n was that the input size is uh, decreasing by constant factor, right? For example, binary search reduces the array size by half every single time. Now, combining these two together, right? That is what gives us the linear rhythmic time. Means for each of the n elements, algorithm does log n work. So think about this, right? Now in log n, I was kind of splitting the array by half or by a constant factor. By order of n means basically I'm checking every single element, right? Combining these together, this is what it kind of gives us, right? For each of the n element, my algorithm is doing a log n work. So for example, for each of the n element, right, my algorithm needs log n operations. It's performing log n number of operations, right? I hope that is kind of making sense. So one of the examples is, don't worry, we will cover this merge sort in detail in the series, right? But for now, I'll just give you a quick overview, right? Merge sort is basically a sorting algorithm, right? Sorting based on ascending or descending order. This is what the algorithm does. So what it does is it divides the array and then it combines it again. So it basically splits the array into multiple parts and then it combines those parts again and again until we have the entire sorted array, right? So what happens is that dividing this array takes log n number of operations, right? This OPS basically means operations. So what my point is that dividing the array into multiple parts, right? That part basically takes log n time. But then we have to combine all those different parts together again. It's kind of like you have already made a puzzle, right? But you break every single part and then you're trying to build it back again, right? And that is kind of how merge sort works. So you divide it, which is kind of log n, right? Just like I said, dividing is kind of like splitting by a constant factor. And then combining basically takes n operations, right? When you combine, you look at all the parts and all the elements inside those parts individually, and then you compare them, right? Don't worry too much if you don't understand the merge sort, but the point is that we divide the array, which takes log n operations, and then we have to combine it where we look at every single element, right? And that takes n operations. So this gives us n multiplied by log n operations. Right, I hope that is kind of making sense. We have other algorithms as well, which kind of take n log n operations, or I should say n log n time. So don't worry too much. We will cover those examples in detail, right? Okay. Then we have the quadratic time. Once again, very easy to understand. Algorithms that compare or process every pair of elements, right? So a lot of algorithms are looking at every pair of elements, and one of the examples is this one, right? So what we are doing is we are creating a for loop inside a for loop, and then we are printing the I and j values. So think about what's going to happen is, right? So I'm going to print 0, 0, 0, 1, 0, 2, 0, 3 until whatever 0n is, right? And then this is going to grow in this place as well, right? It's kind of like 0, 1, 0, 2 until the very end. So I should say, sorry, should be 1, 0, 2, 0, n 0. Right, so think about this, right? This is how many number of elements will be printed. They're all going to go down, right? So for example, in the first part, when I first enter the loop, it's going to print 0, 0, right? Then it's going to print 0, 1, 0, 2, 0, 3, 0, 4 until 0n. And then again, it's going to start at 1, 0, 1, 1, 1, 2, 1, 3, then 2, 0, 2, 1, 2, 2, 2, 3. But the point is that when I have n elements, I'm printing n square values, right? N multiplied by n values. So think about this. I'm printing I and I'm printing j as well. But whatever the input is, so let's say the input is 4, right? In this case, then I would be printing 4 multiplied by 4, 16 values, right? So that means 16 number of operations. Or if it was, let's say, 3, then it would be 3 multiplied by 3, meaning 9 number of operations, right? So this one is very simple to understand. Quadratic time, basically comparing or processing every pair of elements. Once again, we're going to look at a lot of examples of quadratic time as well, and basically every single time that we're going to cover in this video, right? So now let's move on to the next part. Okay, now let's try to understand the cubic time and the exponential time, right? So cubic time is basically, it takes n square amount of time, right? So just like we understood quadratic time, in which we had 2 for loops, right? 2 nested for loops. Cubic time is kind of like, one of example would be 3 nested for loops, right? So it's kind of like one for loop inside another, right? A lot of algorithms take cubic time as well, but this is again a lot of time, right? Algorithms with n cube and exponential time are way too slow, right? The point is that for these algorithms, as the value of n is increasing, their time is increasing by cubic time, right? I hope that is kind of making sense. So this is kind of just like n square, the quadratic time, but it's just n cube instead, right? Okay, the next one is the exponential time. Now this is important to understand, right? So the point is that this algorithm doubles their work for every extra input. Now if you remember for the log n, right? Log n was kind of reducing its work by half, right? Or I should say by a constant factor, right? So, but in this algorithm, it's kind of doing the opposite of log n time, right? These type of algorithms are kind of doing the opposite. So the algorithm doubles their work for every extra input. So let's say I have n inputs, right? Let's say I have 8 inputs. Then what it would mean is that it's going to double its work for every extra input that you're having. So if I have values like 1, 2, 3, 4, 5, 6, let's say I have this input, right? It's going to perform 2 operations for this one, 2 operations for this one, and 2 operations for every single value, right? And hence we say that it's going to be 2 to the power of n. It's performing 2 operations for every single element or input we have, right? So algorithm doubles their work for every extra input. That is kind of what it means, right? So it's kind of like for every input value, it's performing 2 operations. So think about this, right? Now, if you look at this part over here, I have this Fibonacci sequence. This is what we call the Fibonacci and sequence. Don't worry too much. But if you look at this algorithm, right, what it's doing is, if n value is less than equal to 1, it returns it. Otherwise, it calls the function 2 times. And it's going to call the Fibonacci n minus 1. It's going to call n minus 2 as well. So based on how many number of values I have, it's calling it one more time. So it's kind of like I start with n. It calls n minus 1, n minus 2. This leads in another call. This is going to be n minus 2, n minus 3, and then it's going to be n minus 3, n minus 4. Right? This is kind of that this graph is kind of growing exponentially, right? It's going exponentially in this way. So kind of I should say it's kind of like this. So if I have time and I have n, as n increases, the exponentially this leads to exponential growth in the graph. Right? So the basic point is that the algorithm is doubling its work for every extra input. So think about this, right? 2 to the power of n. 2 to the power of 1 is 2. 2 to the power of 2 is 4. This is fine until this point. But when it reaches 2 to the power of 10 or 2 to the power of 20, these are extreme values, right? That means a lot of operations are involved. So we generally try to avoid exponential time algorithms, but in some cases we can't really do anything, right? Some examples or some algorithms do take exponential time, right? Okay, now let's move on to the last one, which is the factorial time. Okay, now let's try to understand the last one, which is the slowest one, and it is factorial time, right? So it is the slowest one typically seen in brute force permutations, right? We're talking about the n factorial time, right? So just to give you guys a quick overview of what is factorial. So when I talk about 3 factorial, right? 3 factorial would mean 3 multiplied by 2 multiplied by 1. So 4 factorial would be 4 into 3 into 2 into 1. So whatever the input size is, right? we're saying that this algorithm is actually taking n, whatever the input is, factorial of it, right? That amount of time. So think about this, right? Even for 4, it might be small, but as the value increases, right? For values like 10, 20, their factorials are huge, right? They take a lot of operations. So it is typically seen in brute force permutations. An example is generating all permutations of n items, right? So just to give you guys a quick overview of what is permutation, let's say I give you this array, right? I give you A, B, and C. Let's say I give you 3 values and I ask you form all the different possible combinations of A, B, C, right? So one could be A, B, C, other one could be B, A, C, it could be C, A, B. We're asking about all the possible combinations we can form, right? And how much it would be? It would be 3 multiplied by 2 multiplied by 1, which is actually equal to 6. Now think about this question, right? Generating permutations of n items. Let's say if you're asked generate permutations for 10 different items, right? That would mean n factorial, it would be equal to this many operations, right? And that's a lot. And that is why this is basically the slowest one, and this is the worst possible time we can have for an algorithm, right? So we will look at one of the examples for this factorial time as well, but one very general example would be generating all permutations, right? So that's pretty much it for this lecture. I've given this summary over here, so let's just quickly go through the summary as well. So O1 is just constant time, right? Once again, constant time meaning doesn't matter whatever the input is, the amount of time it takes is going to remain constant. So I don't really care if the input size is 500, 600, 700, the amount of time my algorithm takes is going to be the same, right? Second one is order of log n. What this means is that my algorithm is kind of dividing its work into half, or I should say by a constant factor, right? For example, in binary search, it basically reduces the array size by half every single time, right? And so it means basically it takes log n time. Third one is order of n, which is kind of linear time. So what this means is that my time is directly proportional to the amount of elements I have. So it could be that if I am trying to print all the values in an array, or I should say I'm printing all the values until n. So as the n value increases, if it is 500, 600, I would have to perform that many operations, right? Third one is, the fourth one is n log n. This is just like the combination of log n and n in this case, right? So in very simple words, the easy way to understand it is, right, for every single element, right, I'm performing log n operations, right? Fourth one, then we have O n square meaning quadratic time. So it's kind of like, um, we have double for loop, or I should say a nested for loop, right? So in the case that you're performing, for every single operation, you're performing other operation as well, right? So for example, you're asked to print, just like we saw in the example, right? Having the nested for loop. This again is kind of like very easy to understand. N cube would again be like a 3 for loop or 3 nested for loop, right? Next, we have the order of 2n, which is the exponential time. This is kind of the opposite of order of log n. While log n was reducing its problem by half or a constant factor, order of 2n doubles its work every single time. For every single extra input, it's going to double its time, right? So that is why it is basically order of 2 to the power of n. And then we have order of n factorial, and this is the worst case scenario possible, right? So this is basically when we are trying to find all the permutation combinations, there's another problem called the traveling salesman problem, which we will look into, and it takes n factorial time, right? So this is the order, this is the best possible time, and it goes in this way, right? Once again, we are trying our best to have algorithms which lie on this side, right? Like to bring them towards the left side of this sentence over here, right? So I hope you were able to understand the different time complexities. In the next lecture, we will move on to space complexity, right? And once again, I would really appreciate if you share it with your friends and people that you know. And if you subscribe and like my videos, that would be awesome.